For this last part of this review lecture, we're going to talk about inferential statistics for contingency tables, correlation, and regression. So recall that there are two kinds of chi-squared tests. There's the chi-squared one-way goodness of fit test, in which we answer the question, does an observed frequency distribution, an observed distribution of counts, does it fit some claimed distribution in the population? The chi-squared two-way test for independence asks, are two categorical variables related to each other in the population? Are they dependent or independent of each other? Here's a key point to keep in mind about these two chi-square tests. Right? If you're just interested in saying something about a sample, and you have a sample of data, you don't need to conduct these tests. You can just say, if somebody's saying, in this sample, I think the distribution is this, right? You can just compare the frequency distribution with some claim distribution in the sample. Or equivalently, if you have the population, you don't need to conduct these tests. These tests are appropriate when you want to use a random sample of data to say something or test a claim about some population characteristic. Right? So let's look at these two major chi-square tests. The chi-square one-way goodness of fit test. Okay, there are several preliminary conditions, but the steps are the basics of the same. We compute the chi-square test statistic when we conduct the chi-square one-way goodness of fit test, but the chi-square test statistic we can compare it to a critical value, or we can calculate or compute a p-value based on this chi-square test statistic. For this course, we'll focus on p-values. It's commonly used in the literature. The one-way goodness of fit test, it's based on expected counts. To calculate the chi-square test statistic, we first need to obtain the expected cell counts under the assumption of the null hypothesis. So the way we do this is we take the sample size and multiply by the claimed proportion for each category. So this one-way goodness of fit test, it's appropriate when we have a single categorical variable with multiple levels, and somebody's making claims about this distribution of this categorical variable in the population. We want to grab these observed counts, and also we want to compare it with these expected cell counts based on the claimed proportions in the population. Right? The chi-square test statistic looks like this. Okay? It's a function of the expected minus the observed counts squared divided by the expected counts. And you add these values up, these terms up, for each of the k levels of our categorical variable. This is similar to before. This test statistic tells us how far our actual or observed distribution of counts is from the claimed or expected distribution of counts. Right? This chi-square test statistic, it lies on the chi-square distribution model. The chi-square distribution model is a probability distribution model just like the normal distribution model or the t-distribution model. We use it to make inferences for the chi-square one-way and two-way goodness of fit test. So we're going to use statistical software to interpret the chi-square one-way of goodness of fit test. And here, in this particular instance, when somebody's making a claim about a given population distribution, we get a p-value that is 0.5. So we fail to reject the null at the alpha 0.05 level. Right? We could also use the chi-square test statistic and interpret that. Right? The other major chi-square test is the chi-square two-way test for independence. Right? It's slightly different. It's used in the example or case in which we have a random sample of data, and we have two categorical variables, and we want to see, are these independent or dependent in the population? Again, if you had a population of data, you could just look at the contingency table and see if they're independent or dependent. But since we have a random sample, it could be due to random sampling variability, if we observe that in the sample they're independent or dependent. So we want to make an inference. We want to say, given the sample of data, what can we say about the population in terms of the relationship between these two variables? Are they related or not? So it's a similar sort of process. We have the 5 steps. The chi-square two-way test for independence is based on a chi-square test statistic that lies on the chi-square distribution. What's different about the two-way test, right, and that two-way refers to the fact that we have two variables, two categorical variables. The one-way chi-square test is based only on one variable. But the big difference has to do with the expected counts. To calculate the counts for the chi-square test statistic for a two-way test for independence, right, we use a slightly different formula. The expected cell counts are a function of the row total of the contingency table times the column total divided by the overall total. Right? This is simply obtained from a contingency table. The expected cell counts are simply a function of the fact that we now have two variables, two categorical variables, when we want to calculate the expected cell counts. The chi-square test statistic itself has the same form. Right? It's just the expected counts minus the observed counts squared divided by the expected counts summed up for each of those cells. So here's the statistical software output for the chi-squared two-way test for independence. So we get this p-value, and we're going to fail to reject the null at the alpha 0.05 level. Okay? So in this case, all right, we reject the null. All right? So with that, we cover the basics of the one-way and two-way chi-square tests for independence and for goodness of fit.